Hello and welcome everyone. My name is Peter Robinson and this is the Ethereum Engineering Group Meetup. Today we've got Antonio and Michele here who are going to talk about the intersection of blockchain and AI and some interesting technology that they have been working on. So before we dive into slides, I don't know, Michele, do you want to go first? Do you want to explain, give a bit of background quickly? Who are you? Why are you here? And, and then flip it over to Antonio.
Sure. Yeah. So who am I? My name is Michele, and my background is computer science. Worked in research a bit around database technologies, and then jumped into robotics. Ended up doing more and more data science, machine learning, and since more or less 1 year, I'm working with Warden Labs on how to bring AI on chain. And yeah, that's me in a nutshell. Antonio, to you.
Hello, everyone. My name is Antonio, and I'm a software engineer with a few years of experience. To keep it short, I started my journey in the blockchain industry by joining Tendermint, the company behind Cosmos and the Cosmos SDK. And then I moved on to Warden to basically make our own blockchain. And as Michele said, we are trying to bring AI into this world. Yeah, I would keep it that way.
Okay. So, well, thank you both for joining today. And look, why don't you present your slides? And, are you happy how would you like to take questions? Should we wait to the end of each section, dive in, and whenever, just put them in the chat, or wait to the end? How would you like to handle it?
So since we are a small group, we can take the opportunity to maximize interaction. So yeah, please let's stop the presentation at any point. Let's try to have it as a conversation as much as we can. So whenever there's something interesting to dive into, please stop us.
Okay, sounds good. All right, well, please, both of you, take it away.
Great. I'm gonna share my slides. Sorry, go ahead, Antonio.
No, yeah, share your screen if you can.
Yeah, it should work. All right, you can see it, right?
Yep.
Perfect. Let me. Okay, perfect. So again, thank you everyone for joining. And yeah, today we're going to talk about this new technology we envisioned 6+ months ago, and recently also published a white paper on it. And we are now ready to talk about it. So statistical proof of execution, in short, SPEX. And let's dive into it. So what is the main motivation behind this work? Well, for both on-chain and off-chain applications, you might want to request to a black box some kind of output, right? Which could be an AI model, and you want to get back some predictions, right? So let's say that we want to consume some predictions from an AI model, and me, the submitter, I request to another system, the solver, to produce those predictions for me, as we see here in the diagram. And then, yeah, again, I might then consume these predictions on chain or off chain. Well, this is great, but I also want to trust these predictions, right? So this is why in this very simple scheme, we might also want to introduce a third party, the verifier, that given some proof of the based on the predictions produced, it can tell me if those predictions should be trusted or not. So this is at very high level the motivation behind this work, and to give it a bit more breadth. in terms of motivations, this is an increased automation in decision making in general, driven by ML inference, which really is often just a black box. We cannot really inspect much. There's a lack of verification in using this technology, with an increase in potential errors, biases, manipulation. We just don't know. It's an opaque box. We don't control. We cannot inspect, right? So as we saw before, all kinds of questions come up. Does this REST API always return the same value if I feed in the same inputs? Is the forecast consistent with the model specification? Can I verify somehow that the outputs are correct, that have been obtained or computed using the intended model? Is this result, is this text generated by the LLM I'm paying for, and potentially not a cheaper one? So all these questions boil down to verify what was the computational process that generated the output. And yeah, here we have the supporting article, which we will extract some content for this presentation. But yeah, for questions or deep dives, this is really a good resource. I invite everyone to look at. We probably cover 1/5 of the white paper in this talk. So yeah, so if you are interested in more details, let's invite you to have a look at it. So let's start from some preliminary definitions, and this is very important to make sure we are on the same ground and we understand each other. So let's say that we have a certain task, which can be any compute pipeline, could be ETS, data transformations, or machine learning, training workloads, AI inference, LLM workloads, any kind of REST APIs. So in general, any task which provides some inputs, we expect some outputs out. And we have also a specification function, F. F is a function that serves as a reference implementation for the task, which we also can use to verify the correctness of the outputs, right? So we can verify if the outputs are correct, making sure that if we do use the function F as implementation, we would obtain the same result. So it serves as a correctness criterion. And yeah, then we have the solver S, which is an executor for the tasks. And might have an incentive to manipulate or alter outputs. As we saw before, the solver is a party that provides the outputs, provided the inputs. And lastly is the verifier, is again an executor that verifies the correctness of the outputs of certain solver S accordingly to the specification function F. And let's briefly talk about the behaviors which we can have in the system. So we have honest executors that carry out the computation correctly and fully, and maintaining accuracy, integrity, so not manipulating outputs. We can trust honest executors. Then we have lazy executors that might skip or approximate some steps to reduce effort. They don't have any strategic intent to alter the results. They just want to skip or approximate some steps to reduce effort. We have then adversarial executors that might have a hidden intent to manipulate computations, and potentially also incurring in higher costs, right? So to make sure that, not to make sure, but to try to manipulate the outputs, they might do the best, even doing more work than required from an honest executor, for example. And altogether, lazy and adversarial executors are grouped into dishonest executors. So let's, I don't see the question, so if there are questions in the chat, please stop me. Let's now briefly provide a more formal definition of the problem we want to work on, introduce here. So verifiable computing, given a task T that is executed repeatedly with potentially varying inputs. The task T, as we saw before, it's any computational pipeline. The function S produces as output R, and along with the cryptographic proof P, right? So the output is R plus a cryptographic proof P, which then function V can use to verify the correctness of the output. And function S returns runs on solver S, while function V runs on verifier V. Now here we have verifier V that is always honest, right? So while the solver S might be lazy or adversarial, the objective here is to guarantee the correctness of the output R with a certain confidence level, while minimizing the combined memory and computational cost for S and V. Okay, so the solver does the full computation, and then the verifier verifies it. And again, verifier is always honest. Solver might be lazy or adversarial. Let's now introduce SPEX. And SPEX is a sampling-based protocol, which is quite flexible and efficient, as we will see in a second. And there are a few extensions which we might talk through in the QA time for handling non-deterministic workloads, like with GPU inference and embeddings. And we also have a reference open source implementation, Warden SPEX, which you can pip install or UV install and experiment with. Now let's quickly overview different approaches for verifiable computing, for machine learning in particular. So TML, let's start from the first one. TML, machine learning on trusted executed environments. It's based on hardware enclaves, isolated environments, providing data confidentiality and code integrity. What are the goals here? Well, you have a time overhead, 30%, depending on the workload, and usually in enclaves you have limited memory availability, right? So you do have some constraints on what you can actually do inside hardware enclaves, inside these, and you must also trust the hardware manufacturer, right, to keep, for example, root keys confidential and secret. This might always not be true. For example, we had this big issue in 2024 where Intel SGX root keys got compromised for the Intel SGX solution. So it is safe until it is not, right? So you have to trust this third party to keep the root keys private and safe. Then we have ZKML, zero knowledge machine learning, which is really a fantastic technology. It ensures the correctness of the outputs without exposing exactly how the computation works or what is the computation being carried out, and keeping input output encrypted all the time, so they are never disclosed. Cons, it's extremely slower, more than 10,000 times slower than just computing the task without just computing the task. There's also a long setup time, so compilation and quite complex. So you cannot just take something that you run regularly and expect it to run inside a spatial environment of some sort. You have really to take the code, adapt it, recompile it, and it doesn't generally support all machine learning AI models out of the box. So nice, but it might not be always a great fit. Then we have optimistic machine learning, which uses a challenger phase, challenger time, and partial re-execution of the task inside a virtual machine. Now here, there's a time override, which is basically the confidence you want in the outputs. The higher the confidence, the higher the compute overhead. And the compute overhead happens inside the virtual machine. So there's also the added cost of running the task inside the virtual machine. Cons, well, there's a challenge period prior to finalization, which adds up to the compute overhead and requires also recompilation and VM execution. Why? Because the original task is not executed in the VM, but in case the outputs get challenged, it gets executed inside a VM. So yeah. And again, no support for any general machine learning AI model. Why? Because you always need this adaptation, and the VM itself might not be capable enough to run any kind of model. Then we have SPEX, our proposal, which relies on cryptographic proofs for computation and sampled verification. Again, sampling in this regard is similar to optimistic machine learning, right? So we do sample what part of the computation we want to execute. And the confidence here is a percentage of the compute overhead. Cons, there's no confidentiality of inputs and outputs if we compare it to TKML. Also with OPML, we don't have them. And but we don't have we don't need to run it inside a virtual machine, so we have some benefits out of this. And let's dive into how the SPEX protocol can protect against lazy solvers in particular. For adversarial solvers, things are a bit different. They are discussed in the white paper, and we can also touch point on them in the QA time. Very briefly, hashing functions. I guess everyone here is familiar with hashing functions, but anyways, so let's say I will quickly introduce them. So we have some inputs, M0 to M4, and each message can be hashed through a function, hashing function. And these functions, their special purpose is to map data of arbitrary size to fixed size values. For example, integers. Okay, so input can be text, output is integers, for example. And how do we use hashing functions in SPEX? Well, before answering that, we need to also introduce Bloom filters, which are space-efficient probabilistic data structures for a set membership. So again, an example, let's say that we have a set with X, Y, Z. X, Y, Z are inserted in the data structure by computing the hash, which returns 3 integers. And these integers are treated as offsets in a bit array, which are set to 1. And the others are defaulted to 0. And whenever we need to check if a value is present in the set or not, we compute the hashing functions on the value and check if the bits are the corresponding offsets are set to 1. For example, here we have W, which in 2 cases we see bits are set to 1. Third one, it's not. So with 3 hashing functions, 2 would match, but 3 we see that there's actually a 0 in there. So we can say that W is not part of the set, right? As you can see, the more hashing functions you consider, the stronger guarantees you get from the Bloom filter. Now let's also introduce computational pipelines. So computational pipelines very broadly transform inputs S in outputs E, right? And the flow of computational pipelines can be sequential or parallel. Here we see 2 sequential, we see 2 parallel flows, A1, A2, A3, and B1 to B3. And what is interesting here is that to to compute B3, we don't really need to compute A2, but we do need to compute B1, B2, right? So there's a dependency between states here, and only a subset of the states preceding a certain state are required to reach it. How do they fit into ML AI computational pipelines? Well, in terms of sequential processing, usually feature extraction or data preparation fit into sequential processing, while for parallel processing, we have batch inference, simulations, ensemble models, all kinds of subtasks that can be executed in parallel with any with no dependency between individual subtasks. And the intuition, so the main idea behind SPEX is to use Bloom filters to hash the state of the computation and check if a certain state has been reached or not. So in machine learning AI pipelines, states are then can be mapped to inputs, model weights, or intermediate results, outputs. So any state in the computation, and Bloom filters can serve as a computation certificate. Right? They can prove that we indeed executed the process accordingly to specification. And we can answer then questions: did we reach A3 in the evaluation or not? By checking if a certain state is present in the Bloom filter or not. If we bring all things together and look back at the diagram we saw before, here we can see how this all fits together, right? So we have the submitter, which requests inference given a certain input X to the solver, which returns back the predictions Y and the proof P. And the submitter can then prove that the solver did at least followed the specification for the task by providing the proof P and the input X to a certain a verifier for verification. Here we see a quick example of it for batch inference. So let's have a look here. We have the input X is structured with batch inference. You have multiple inputs grouped together, right? So X0 to X9, they are all independent. And when we ask for a prediction to the solver will produce Y0 to Y9 independently, right? So X0 to Y0, X5 to Y5, and so on independently. But the solver will also create a Bloom filter, inserting all the predictions inside the proof P. Okay, and at this point, at verification time, once we provide the proof P and the inputs X to the verifier can sample any subset of the inputs in X and check if the prediction is indeed in part of the proof or not. So in this way, it can verify and validate the outputs of the solver. Now, a few comments on what we just discussed. The verifier is picking randomly, is selecting randomly a subset of the inputs, right? Which is why the overhead is proportional to how much confidence you want in the outputs. If you want 100 confidence in the outputs, you basically execute 100% of the computation and so on. So, but what is interesting here is that there's no time overhead. The verification process can happen in parallel to the solver process. Only when the proof P is produced by the solver, the verifier can then check if the pre-computed items are present in there. So this is just basically one step at the end where the two are joined, and the solver doesn't know which predictions the verifier is gonna check, right? So which is important because in this way the solver cannot optimize cheating. And as you can imagine, it works best with parallel flows because the verifier can bypass prior independent states. With sequential flows, it still works, but then you get to an overall higher overhead. The considerations we don't have time to discuss now, but there are a few nice examples covering this in the white paper. And I now handle it to Antonio. Thank you.
Yes, thanks, Michele. Do you want to share my screen, or do you want to follow me to change slides for me? Well, I don't know.
Before we dive into your section, could I ask a question?
Yeah.
So you had parallel execution happening and then parallel outputs, that then went into the what do you call it? The filter at the end. And is there a limit to how much parallel work can be done? Would it make it that all the bits are one, so you can't really differentiate what has been executed and what hasn't? Is there some limit?
Yeah, so this is a good question. So Bloom filters. So Bloom filters are additive. So you can compute subsets of tasks independently and obtaining multiple Bloom filters, and then you can also take the union of Bloom filters to obtain the result, right? So that is also an interesting property. A lazy solver might feed you with a proof that is full of ones, right? So that then the verifier would always find everything. This is why it is important to verify the ratio of false positives in your Bloom filter. So when we create the Bloom filter, we specify what is the expected rate of false positives we have, right? And in this way we can size accordingly the Bloom filter, and at verification time we can also check, we can also estimate that rate and verify that it is actually within reasonable bounds. So if you feed a Bloom filter filled with ones, we can then check that the estimated false rate of false positives is wrong, and we can detect a violation of the Bloom filter.
Okay, that makes sense. All right, well, thank you. Yeah, so over to you, Antonio.
Sure, thank you. So
I can handle the slides, so I let you just let me know when I have to switch slide. Sorry.
Okay. So I'm going to talk a bit about the concrete use case of why we built SPEX. So Michele at the beginning talk a bit about motivation behind it, and I'm going to introduce our blockchain, if you bear with me, just for introducing like a real world use case that we have for it. So Warden is a layer 1 blockchain, and we have this concept of plugins, which is some sort of like an extensible Oracle system. Next slide, please, Michele. We built this blockchain with Cosmos SDK. It's a layer 1. We have proof of stake, let's say classic proof of stake of Cosmos, and we have like 30 validators in our network. We also are EVM compatible. We have an EVM running thanks to the Cosmos EVM module. And we have this concept of plugins, which is something unique to our blockchain. They can be used by smart contracts developer using our precompiled contracts. And basically plugins are a way for any validators to plug in additional features to the network without requiring a full network upgrade. So each validator individually can decide which plugin to run. I'll dive deeper in a second. And SPEX is one strategy for building these sort of plugins that can be verified by other validators. Next slide, please. You can see each plugin as an oracle, independent from the others. And as I said, each one of the validator can decide which plugin to run. If you have at least one validator running a plugin, that will make the validator the executor. The rest of the validators can be the verifiers for it. So for each request that a user makes, requesting something from a specific plugin, the blockchain itself deterministically choose one of the validator as a solver, while the rest can be the verifiers that we talked about for SPEX. I also wanted to mention that the runtime for this plugin is fully asynchronous. So the user will request something at a block age, the response will arrive at a later block, and then the verifiers will include their basically Boolean votes on yet another block. Next slide. And to keep it simple, we developed this very minimal interface for building a plugin that contains only a couple methods. One is for executing something. And as you can see here, we talk only about a blob of bytes, so as an input and as an output. And the second method is verify, which is, again, it takes the input and the output as blob of bytes and just returns a Boolean, you can say. The main idea is to keep it simple for keep it generic for different strategies to be applied. One of those strategies for verification is SPEX. And as of today in our chain, we have plugins as part of the main binary implementation. So they're basically written in Go and part of our main binary. But we are building a platform for running this plugin as WebAssembly binaries. So they will be developed, compiled to WebAssembly, shipped to validators' machines, and this will be more like a plugin, as you can imagine. Next slide, please. So I wanted to give the look and feeling of using one of those plugins. One of those is called HTTP. And it, as the name suggests, it lets you make HTTP requests from your smart contract. This is a Solidity function. We have this precompiled contract for it. So we develop this HTTP.request type. You can set some fields for it, like the URL and the HTTP method. You can include, for example, a payload for your request. And then you use our other precompiled contract, that is the async contract, that lets you specify which one of the plugin to call. This name is a unique identifier for it. And then depending on the plugin you are invoking, you need to provide the input as a blob of bytes. In this case, we take the HTTP request type, we encode it using ABI, which is very convenient to do it in Solidity. And we also pass a third parameter, which is the callback address of the contract that will be invoked automatically when the result is ready. As I said, our runtime is asynchronous, so we need a way to pass the result back. And callbacks are convenient instead of periodically checking if your result is ready. And this is all handled automatically by our blockchain. Next slide, please. Yeah, this is the Solidity function, the callback Solidity function that will be invoked whenever the result is ready. The first line fetches the asynchronous task by its ID that was returned in the previous slide. And here we can see that the task contains a result and an output. Again, this is a blob of bytes. We need to decode it into something. And this is plugin specific. So we decode it using ABI again into this HTTP.response structure so that we can read the status code, for example, for the HTTP request and the body of it. We also provide, for example, a JSON precompile that lets you extract the specific fields that you want from the JSON, which is convenient to use from Solidity, of course. And yeah, this is mostly it for the HTTP plugin. Next slide, please. just a couple mentioned here. For example, whenever you request an HTTP request, as I said, the blockchain will choose one of the validators that has the HTTP plugin enabled, and that will be the solver. So in a way, it's centralized. You don't get to choose which one of the validators, and not all of them will run your HTTP request. You have to trust it, right? One way of using SPEX could be to batch and requests of different users even, and to take a sample of it. So to take a subset of these requests to verify them. This works under the assumption that the HTTP requests we are making are deterministic. So in a way that whenever you make the same request, you get the same output. So these are kind of the assumptions for making the HTTP plugin verifiable. Next slide. We started from this HTTP plugin as a sandbox, as a way for trying out different strategies and also to sparkle creativity in smart contract development to see what API you would use inside your smart contract. And we also came up with another plugin. So once you are done with that part, you can develop your own specific plugin. In this case, for example, we built an HTTP server that uses a neural network under the hood for predicting the price of 100+ tokens. And this is verifiable with SPEX in another way. So let me explain. Whenever you use this price spread plugin, you specify a list of tokens that you want to predict and a date in the future. What happens is that using SPEX, the other validators that are running the same plugin will be able to sample a subset of tokens. Instead of repredict all the tokens that you asked, they will only predict a subset of it. And they will use SPEX with the Bloom filters that Michele explained to check if this subset of tokens was predicted correctly. And so the validator that was chosen as a solver is not trying to fake some data. And that was it. Next slide, I think it's the end. Thank you.
You don't thank us, we're thanking you. So that was great. And I know I've put a few questions in my own little notes, but before I ask any, is there any, Lecky and others, are there any questions from the audience? Okay. All right, it's left to me to ask you the tricky questions. So HTTP outward bound requests from a blockchain validator node. What happened, you know how in the internet there are certain IP address ranges which are specifically do very slow TCP/IP, specifically to try and catch spam bots and to really slow them down. So say someone put in a request to some malicious part of the internet address range where it was going to take a very long time for the HTTP request to come back and even the TCP/IP to work. Would that slow the validator node down, or is that all handled asynchronously? How does that work?
So everything is handled asynchronously. If you want the technical details, they basically run the entire blockchain is written in Go, and this is handled by using Go routines. So they are separate from the main blockchain execution flow. Each validator can enable one of those plugins. One of them is HTTP and can configure it. So I expect to configure certain timeouts. Mm-hmm. And if the request doesn't go through inside this timeout, it just fails. And each validator I expect to be configuring their plugin independently. So if you, first of all, you can decide if you want to do it or not, if you want to run the HTTP request or not. Second, you can configure things such as timeouts to handle this. In any case, the blockchain, the block production, and the validator normal work is not impacted by it.
Okay, which is what I think everyone, myself and everyone else would have thought. But good to check. And
yeah, it's a good question.
yeah, yeah. So, say if you were doing a HTTP request to an oracle, the whole idea of an oracle is that it will change at some point. Because if it was just a constant, you wouldn't need to be asking what the value is. But that sort of means that surely there will be times when the the executor will go off, get a value, and says Ethereum's worth this amount, and then the verifier will go off like a second or two later and get a different value simply because the value has changed. Does that sort of result in an error, and then all those requests need to be retried, or how does that work?
Yeah, so that depends on the use case. So if you are requesting something from an API like that, it becomes very hard to verify the response. And in this case, I think of HTTP requests as a way of, as I said, trying out ideas. So let me take a step back. If the API allows it, it would be great to have some sort of timestamp parameter in the request, such as to make it deterministic, right? And not requesting like the now price, which changes every maybe even milliseconds. So it's impossible to receive the same response twice.
Yeah,
But
okay.
if you have no control over it, you can either build your own HTTP proxy, so you can build your own server, run it, and make the HTTP request to your proxy, but this centralize the source of truth, right? So you no longer have to trust CoinGecko or whatever API you are calling. You have to trust your relay, which is not ideal.
Yeah.
If you can leverage specific knowledge of the HTTP request that you're making, I would suggest to build your own plugin so that you can plug in your verification logic as well. So you have to implement the verify method, and that can be done in many different ways. For example, in the case of price oracles, what's typically done is to for example, to fetch prices from different sources and then to average down to minimize the shifting between the prices, and then to have some sort of acceptable threshold. So if the requests are coming through in different times, like in different seconds, you can have a margin of threshold that you would accept. But that needs to be done in your plugin, building your own verification logic. And the HTTP plugin that we provide today is more generic. It's more meant to be used for, for testing out ideas, for sandboxing, and see what you can build inside your smart contract.
Oh, look, it's a great starting point, I think, for people. Another question. So it's statistical, proofs. So I guess you're going to try multiple bits to see, so you're going to have multiple requests, and then you're going to have the Bloom filter. And I'm just trying to think how much is it? How many samples do you need to do to be certain, like that say 1 in a million chance that everything's okay? Is it just a binary 2 to the 20? So you do try out 20 things, and if you have done 20 samples, then you feel you're right? Or and maybe I'm thinking about this in the wrong way.
This is this is actually a correct way. So maybe I can take this one. as a developer, you have an expectation of what is the confidence in the outcome you get from the task, right? So it could be I want this task is super important. I want 100% confidence. I'm happy to pay more for this. So you are basically asking for a full recompute of the entire task for verification, right? Then you might also be fine with just 20% recomputation, right? So you might be okay with that 20% confidence in the output, which if you keep hitting the same service again and again and again, this also compounds your confidence, not in the specific answer, but in the party that provides the answer. So this is our reasoning on how we address that. So it is actually a parameter. When you use SPEX, you have to specify what is the confidence you would expect from for the outputs.
Yeah,
Peter, you're on mute.
Yeah, I'm on mute. That makes a lot of sense. And I think the idea of repeated calls gaining confidence, and then I guess it's just a matter of trying to think about the malicious aspect. But that, as you say, you've got information on that in your paper, which we should all get around to reading.
Yeah, definitely. But one comment on this, let's say that you ask for 100 predictions, okay? And you identify, or you ask for 100 orders you should execute as a recommendation, and coin swaps, for example, and you identify one you want to execute, you might verify only that one, right? So you might reproduce selectively only parts of the outputs you're gonna use. So once you have the outputs as a submitter, I can identify, okay, I actually want to use these predictions. Verify, can you please verify these ones for me? Because I'm extremely interested in those ones specifically. And how you can do that, you can specify your threshold of confidence 100%, fitting in just a subset of X and the same Bloom filter. And that's all the evidence the verifier needs to provide 100% confidence in those outputs.
Okay. Yeah, that makes sense. That's good. Yeah, look, it's interesting tech, and I'm sure that everyone who's in the audience today is going to be walking along the street having a coffee tomorrow and then go, but what about this? Which is true for any new technology, isn't it? Yeah. So you've got your own L1. Have you got a test net and a main net, or what's it? How does it? Where are you up to with all of that?
Yeah, we're building our own layer 1. We are at a testnet stage. We actually had a few testnet before, and we are running now our latest one, which is going to be integrated using Hyperlane to the Ethereum mainnet. Also one of our goals is to make these sort of plugins available to the Ethereum mainnet contracts. So using these general message passing technologies that exist like Hyperlane, we would enable these to be used from the Ethereum and other layer 2 networks as well. We are still very much in the testing phase of it. We have the plugin system working on our layer 1, on our testnet, and we're now integrating with the Hyperlane, yes.
Yep.
You can find more info in our website, which is wardenprotocol.org. Actually, if you go to docs.wardenprotocol.org, there are also the information regarding our testnet.
Yeah, sounds good. Sounds good. I'm just trying to think of, I know you're an L1, and I was thinking if you became an L2 on Ethereum, would that help you be more integrated, and hence would it Yeah, but then, like, say if you want it to be OP stack, they want you to use OP stack without changes. But Arbitrum are more flexible, and it's then a matter of, is being an L2 on Ethereum with this experimental technology, would that make it easier for other people on Ethereum in the other L2s use your technology? So I'm not saying, give up on being an L1. I'm just thinking out aloud here. Would it make it easier for people to use, and you might have more traction?
Yeah. It might be. It might be. I cannot say no at this time. We thought about all the possibilities. We are starting as in layer 1 and see how it goes. We also have some, and there are reasons for that. We want to build certain features that are currently that are nice to have if you are building layer 1. For example, I can give you an example. It's a concept of autonomous smart contracts. So smart contracts that can be invoked without user transactions, with user interactions. So they are initiated by the chain code itself. So you, as a user, you prepaid some gas fees in a gas tank, you can imagine, and having your contracts being executed automatically every once in a while. The most simple way is as a cron job, for example. And inside your smart contract, you can leverage these plugins to fetch data from external sources or AI models. And this was let you build your AI agent as a smart contract, which is something that we are not seeing today, at least I'm not aware of. We see AI agents that are Python scripts or running in centralized servers, but that would expand the possibilities, I guess. And these you can make if you have a layer 1. You can have control over the entire stack. You can have control over gas costs or network congestions and all these sort of things. But if eventually we see that it makes more sense to become a layer 2 or to build on another tech stack, I think that we will switch. We want to choose the best technology for our use case as possible.
Yeah, and where best is an ever-changing thing. Yeah. All right, look, it's been really interesting. Could you, there were some final slides. Did you get around to putting them into your slide deck? Yeah, so please, if we could quickly flick to them right at the end, and I'll just go through that stuff for the audience. There is the merch store still. Every now and again, we sell a t-shirt. Every now and again, actually, we sell about 10 t-shirts all in one go. But anyway, next slide. Okay, so next week, Ratan is going to talk about OP Succinct. And so essentially how to use their Succinct ZK system with OP Stack so that you can get a ZK rollup and also an optimistic ZK. I'm going to talk about, I'm actually going to probably split that July the 11th talk into 2. And so one's going to be on Web3 game design, and one's going to be on a very specific contract, a claim contract, which allows you to claim an NFT on-chain, and it uses on-chain random, and how even with on-chain random, it's still actually secure, which is something that 6 months ago I didn't think I was going to be able to achieve. So yeah. And EOF v1.0 is still coming. And so anyway, that's where we're up to talk-wise. Next slide, please. All right, great, thank you. And so if you are watching this on YouTube, go to the meetup and then you can ask tricky questions live. If you're here today, you can watch this on YouTube. There's a Slack workspace where you can ask questions, and as well, there's some example code that some of the talks have, and we'll go into that repo. So Michele and Antonio, thank you very much for your time today and for putting together such a great talk. And so everyone, please give them a round of applause.
Thank you very much for having us. That was
Yeah.
great. Thank you.
Thanks a lot.
Lots of virtual claps there. Yeah. All right. So look, I'm going to, have you guys shared these slides into the Google Drive folder or a
I'm
PDF?
gonna do it right after.
Yeah,
this call
please,
ends.
Yeah, please do. So then what I'll do is I'll be able to share the slides in the description of the YouTube video, and that'll help people understand your technology just that bit better. Yeah. Okay.
Perfect.
All right.
Absolutely.
Brilliant. Thank you. Bye-bye.
Thanks again.
Thanks a lot
Bye-bye.
again. Bye, everyone.